Okay, so I want to welcome you to the second objective of the day. This is actually a call or miscellaneous topics. Within we still have this within the data matrix, the correlation matrix, and the covariance matrix that we started. Of course, in this outline, we've already achieved the data matrix. I've walked you through the covariance matrix, and we just did a correlation matrix. But right now, we want to talk about miscellaneous topics. We want to talk about the cross product calculation. We want to talk about our vectorization. We want to talk about visualizing data. Okay, so let's get started. Okay, now before I go into matrix cross products, I think I need to first tell you our intention here. Let me tell you this. I understand my maths. I understand my statistics perfectly because I actually relate every symbol, every notation to real life. And I normally ask myself before starting a topic, what is the essence or what is the significance of that particular topic in real life? What does it address in real life? Why are we doing it? If I can understand the reason why we're doing it, then I'm actually going to be fine. Now, let me tell you this. Why are we interested in matrix of cross products? We are interested in matrix of cross product because that's actually, that form the backbone of estimation that involve multivariate linear model. You know, I told you the other time, whenever we are seeking for knowledge, we normally need to get information. And if where will the information come from? Information is going to come from data. Okay. If I'm seeking information that has to do with explaining relationship, how does a particular variable causes the other, which means I'm actually I'm having an ambition of testing a causal goal, or I'm seeking an explanatory goal. Okay, I will go by way of regression analysis. If multiple variables are involved, I know you have come across something that will cause cost products. For instance, you want to estimate parameter in a linear regression model. Has anybody come across a beta cap S transpose X inverse, okay, inverse S transpose Y? Has anybody come across that in multiple linear regression model? If I want to estimate parameters in a multiple linear regression model, or maybe I'm actually interested in investigating the effects of some selected variables on a response. Okay, so that is, I'm actually going to make use of that. But if you take a look at part of this formula, there is a cross product. Without us having understanding of a cross product, there's no way we will be able to have our parameters estimated in the model. Okay. Now that's why we want to consider cross product, because cross products actually form the backbone of the method that we use in statistics, to be able to actualize certain intention. Okay, so I want to welcome you to cross product. Now, the cross product is just basically saying I have two matrices, X and Y. I found the transpose of S, and I use the transpose of S to multiply matrix Y. That is what it means. Or I'm doing this. Or I'm using X, a matrix S to multiply the transpose Y. So those are the type of the matrix cross product that we have. Okay, now now that you know, how do we get this in R? I will advise that whatever code that I put on my lecture slide, I will advise you actually try them out. Okay, because as your assignment will be expected to be completed using our software. I'm actually going to release the first assignment today. Okay, I'm going to release the first assignment today. Now let's actually play with computation now. Okay, how do we actually compute cross products? Okay, I'm going to start by simulating data set. If you take a look at what I have here right now, okay, I'm having two matrices. Can you see that? Matrix X. Okay, I'm generating my data set from normal distribution. That's why you see R norm. R norm. I'm generating from a distribution. Okay, so R norm, okay, 2 by, you can see, 2 by 3. Okay, 2 by 3. You can see that. Okay, so if you take a look at that, I generated two matrices, S and Y. And after doing that, I want to get a cross product. Okay, how do I do the transpose in R? Okay, I want to do this. I'm actually looking for this. Okay, X transpose Y. Okay, the transpose is on X. Look at that. Look at here. C into X. That's transpose of X multiplying by Y. Okay, that you have to put this percentage multiplied by percentage notation. Okay, so when you do that, this is going to be the end result. Okay, that is the end result. We also have another way of doing it. You can just write cross product XY. Okay, that would be an easy way. Cross product XY, that will give you this. You can see the two are the same. If you look at the two results, okay, whether I actually do T into S, that, Y, or I do cross product or cross prod, X comma Y, I'm going to have that. Okay, now if you also, what about the other type of the products that I talk about? Okay, this is here, that means S, okay, Y transpose. That's why you see T on Y. Can you see that? That's why you see T on Y. Or you write T cross prod XY. Okay, T cross prod XY, still gonna give you the same result. Okay, it's how to navigate this in R. Okay, that's how to navigate that in R. Okay, now I want to move. I just walk you through cross product, the two type of cross product that we have. Now, I then want to go into vectorization. And this is very, very crucial. Let me tell you this. I want to spare, before I start showing you mathematical aspect of vectorization, I first want to tell you uh, what is the essence of vectorization. Let me tell you this. When you are doing maths, and you may understand your maths, you may understand how to do maths, but if you don't really understand the reason why you are doing maths, then I don't think you understand maths. Okay, I'm going to say that again. You appreciate learning mathematics or learning mathematical related subject when you understand the intentions. What is the essence of vectorization? Look at that. I said turning a matrix into a vector. Why do I need to turn a matrix into a vector? I'm going to tell you why. Number one reason why we turn matrix into a vector is for easy computation. If I want to have easy computation, okay, I'm actually going to turn matrix algebra into uh, linear algebra in a vector form. When you have a matrix algebra, because let me tell you this, operations involving matrix are very difficult to undertake. And that is why we need to vectorize them. I'm going to give you so many reasons. For instance, if you are looking into uh, what I call maybe you have multivariate you're working on a likelihood distribution. You want to estimate parameters. Okay, vectorization will enable your likelihood to be in a closed form. Likelihood function can be in a closed form. It may be in an open form. When it is in an open form, it is very, very difficult to undertake. It may not be tractable. So vectorization, will enable, the likelihood function to be tractable. Not only that, if you want to perform, has anybody heard about gradients? When if you want your derivative, to be tractable as well, okay, having that in a vectorized form will make it so easy. Okay, so there's a lot of benefits. Okay, let me also say this: when you vectorize a matrix, then you are actually having your matrix in a linear system. Do you know that when something is in a linear system, parameter in a linear system can be easily figured out? Okay, now that is a vectorization. Now, the other time, I gave you a matrix X, matrix S that is n by P. Okay, when I vectorize it, oh my God, look at the way it's going to turn into. It's a linear system. That's a vectorization. How do we do this in R? Take a look at what I have right now. If I want to do this in R, take a look at this. I'm simulating a matrix X. Okay. I want to use number 1, 2, 3, 4, 5, 6. And I want the dimension of my matrix is 2 by 3. Okay. Now, this is the resulting matrix. Can you see that? If that is my resulting matrix, how do I vectorize that? Okay. The coding now for vectorize. Oh my God, take a look at that. That is vectorizing C into S. It's just to make it a linear form. 1, 2, 3, 4, 5, 6. Okay. That's what we mean by vectorization. Now I quickly want to walk you through the properties of vectorization. Okay. If I have a if I have a vector A, I'm sorry, matrix A, okay, when I vectorize a transpose, is the same thing as vectorizing the original one, and is the same thing as A situation where A is of m dimensional. Maybe I have A1, A2, A3 up to AM. That's what it means. Okay. And if I vectorize, I can also vectorize cross products. Oh my God. We just talked about cross product the other time. We can also vectorize that. Okay, vectorize. And let me also tell you this. When I vectorize a matrix, how do I preserve dependency among variables? I'm going to say that again. When a matrix is vectorized, how do I preserve dependency among variables? I can preserve, a vectorization we guarantee Kronecker products. Okay, Kronecker products will preserve dependencies. This is whenever you see this sign, that's a Kronecker product. Kronecker. This is look at that. This is what I mean by Kronecker. Can you see that here? That's a Kronecker. So when you vectorize a matrix, okay, you preserve dependency among variables with Kronecker products because vectorization we actually guarantee a Kronecker product structure needed to preserve dependencies among variables. Because let me tell you this, when you do something to data, there's going to be how can we guarantee we have not altered relationship? And that's why the Kronecker product we guarantee we preserve relationship among variables upon vectorization. Okay, so these are just properties. When you talk about vectorize A transpose multiplied by vectorize B is the same thing as a trace of that. You can verify all this property. Okay, now I want to come into the chronicle product of two matrices. Chronicle products of two matrices. I just told you right now what chronicle products. The job of a chronicle product is to preserve dependencies among variables. Okay, upon vectorization. Okay, so I needed to pay attention now. If I have a matrix n by p, and Y, M by Q. I got two different matrices with two different dimensions. How do I obtain a chronicle product? Okay, this is the notation. Okay, S and Y, the chronicle product, you actually, oh my God, if you take a look at what I have here, it's like I'm multiplying each and every element in S by a matrix Y. That's why you see Y all through. And at the end of the day, if I want to know the dimension of the resulting chronicle product, okay, if I want to know the dimension, of course, it's actually what I'm showing you. It is this guy here. It's like the M here multiplying the N here and the Q here multiply that. So that is MN by PQ. Okay. Now I think I showcase some example here. In now, I will advise you try it out now. If I want to, I'm seeing a lot of assignment here. Assignment I'm going to release today. I'm seeing a lot of assignment question. So if I were you, why can't you try that? Okay. Okay. Now, because of my time, I'm actually moving. These are properties of chronicle products. Okay. Properties of chronicle products. Okay. Don't forget whenever you see a sign, this sign, that's a chronicle. That's a chronicle product. So I will advise you go through that. Okay, now we have a common application of vectorization and chronicle. Okay, and I'm actually going to explain more on that when we get to multivariate normal distribution. Okay, if I have a multivariate normal distribution, where I got so many variables that follow. Maybe I have weight, height, blood pressure, or so on like that, and they are all jointly normally distributed, or they follow a particular distribution. You know, if I vectorize the transpose of S, which I'm actually going to call Y, when we vectorize a matrix, we can also figure out the mean and the variance. Okay, now I need you to pay attention now. If Y equal vectorize transpose S, then the mean of Y is what you're seeing right now. Okay, the mean of Y is going to be one in n dimension, multiply, chronicle product of mu, then the variance is going to be that. And here I'm actually showing you the variance of a vectorized transpose of a matrix. And as you can see in the diagonal, you can see each of the covariance structure. And of course, in the off diagonal 0, 0 means they are not related. Okay, so that is what that means. Okay, now I want to come to the last objective of the day, which I call visualizing. Okay, how do I visualize my data set? Let me tell you this. Whenever you have a graphical representation, they're giving a lot of story. Okay, at times I may want to study relationship between variables. But here I want to know the relationship between MPG and HP that can construct a scatter plot. A scatter plot is a diagrammatical plotting of one variable against the other. And why am I interested in that? I actually want to see whether they are positively related or they are negatively related or they do not have any relationship at all. And when you take a look at, and at times when we plot the line, when we plot the relationship, we can also impose the confidence interval bound, okay? Where you're going to have the lower bound of that, the upper bound of that, and at times we also indicate what we call a localized polynomial, the one in the green. And another thing I want to show you here, I know you've seen that before. This is box plots, okay? The box plot of a variable will tell us, the shape, or tell us whether it is skewed or not. Okay, you can see the MPG is skewed. Okay, so you can take a look at that. One is skewed, positively skewed, and the other one is negatively skewed. I don't want to rush you. Whether if I don't finish a material, I'm actually going to add that material to the next material. I don't want to rush you. I'm actually going to stop here. Is there any question before I go today? The first assignment will be released today. Make sure you watch out. And of course, my office hour starts tomorrow. I have my office hour every Tuesday and Thursday on Zoom. Okay, you can be anywhere in the world to attend my office hour. Okay, make sure you all stay safe and enjoy the rest of your day. But for now, everyone.